Good morning. So let's start the lecture summary today. We have lots of things to talk about. So yeah, let's see. So last time we were ending at the introduction of bipartite graphs. So bipartite graphs are graphs such that the nodes can be separated into two groups, such that there are no edges joining vertices from the same group. So this is the bipartite graph. So these two, you can see that we can let them to be in the same group. This is another group, so that between the groups, between vertices in the same group, there are no edges. So all the other edges are joining vertices from different groups. This is not a bipartite graph because no matter how we separate the vertices into two groups, you will see that there must be, so here, let's say we put these two into the same group, this is another one, but then we will see that there are still edge joining vertices from the same group. So this is not a bipartite graph. So we ended with this question. So how do we check if a graph is bipartite or not? Now to check whether a graph is bipartite or not is actually very easy. Yeah, because you can imagine that all the vertices from the same group, we can give them the same color. So let's say these vertices, we color them as black, and these vertices on the right hand side, we color them as white. So in that case, every edge must be joining a black with a white. Now, if it is a bipartite graph, then we must be able to do so. So let's say we color this vertex with black, which implies that if it is bipartite, all the vertices joining to it must be colored in white. And in such a case, all the vertices that is joining this white vertex, it should be colored as black. And then all the vertices joining the black vertices must be white. So if we can somehow color the vertices in this way without any problem, then in such a case, then the graph is a bipartite graph. So this is actually a construction proof. We actually construct a particular way to separate the vertices into two groups and showing that there are no edges between them. Now for this one, let's see this is a bipartite graph or not. So suppose that we color A as black. So in that case, we must have G, E, and C to be white. And with G, C, E to be white, then we must have D and B to be black. Yeah, it is because E is white, then B should be black. Because C is white, then D should be black. But at this point, we have a problem. B is black and D is black. They are already determined, the color. So in that case, we are having an edge joining black with black. So in such a case, then this is not a bipartite graph. So this is capturing what we have just said. If a graph is bipartite, then we must be able to assign the vertices into two colors, such that no adjacent vertices are assigned the same color. And this is true actually for also the other way. So it is if and only if. Okay. And then once we have talked about bipartite graph, we can also define something called a complete bipartite graph. So a complete bipartite graph KMN is a graph such that there are n vertices on one side and there are n vertices on the other side, and it has the maximum number of edges. So we have n black vertices and then n white vertices, and then we have the maximum number of edges. This is also a simple graph. So the maximum number, let's see example. This is a K22. We have 2 here, we have 2 here. And then we join each vertex with another vertex on the other side. So that means that here we must have all these 4 edges. This is the maximum possible number of edges that this graph remains simple. This is K3, 2, 3 vertices on one side, 2 on the other, and then we join all the vertex where one vertex is on the left, one vertex is on the right together with an edge. Okay, so this is K33. So why we call it a complete graph? Because it is having the maximum number of edges. So that's why we call it complete. Nothing that you can edit to make it better. Okay, we next introduce a concept called subgraph. So a graph is a big one. A subgraph is something that we are choosing some vertices and some edges from this graph. Then this will be called a subgraph. Okay, so for instance, this is the original graph, and let's say we pick A, B, D, E, these vertices, and we pick this edge, and this edge, then this is a subgraph. And then the middle one, this is also a subgraph. We don't require that when we pick the vertices, every edge between them, we need to keep it. So this is also a subgraph. So we see that this subgraph is actually a subgraph of this one. And this subgraph is a subgraph of this one. Now how about this? This one is we have A, B, D, E, and then we have an edge joining AD. But we see that in the original graph, there is no such edge. So in this case, this is not a subgraph. Okay. Now subgraph doesn't require that we must have all the edges between the selected nodes to be present. But there is a related concept called induced subgraph. So a subgraph induced by a subset of vertices. So induced subgraph is a special subgraph such that we collect all the vertices and then we also keep all the original edges that is joining these vertices. So in this case, we have A, B, D, E. Then we need to keep edge AE. We need to keep edge BE, also the edge DE. So this is actually the induced subgraph of the original graph based on the subset of vertices A, B, D, E. So this is an induced subgraph, and this is not. Okay, so once the subset of vertices, let us call it U, is known, then the induced subgraph is defined. There is only one of them. And another concept is called the complement of a graph. So the complement of a graph is we have the same set of vertices, but then whenever there is an edge in the original graph, then it will not be an edge in the complement of this graph. On the other hand, when there is no edge between two vertices in the original graph, then in the complement, we will have this edge. So what does that mean? Okay, so the complement graph of G, let us denote this by G bar, will have the vertex set V, the same as G, but for the edge set, it will be all different, okay, such that E and the complement edge, E bar, let's say, they are not having any intersection, but the union of them will be all the edges in the complete graph. Is that okay? So if you are not okay, yeah, go to the OCW recording for more details. So there are examples there. And then we also want to introduce the concept of isomorphic or isomorphism. Iso means the same, morph means shape. So we are talking about graph with the same shape or same structure. So if you look at this graph, it actually looks like this graph. If we rotate this graph, let's say in anti-clockwise by 90 degrees, then we will have this graph. Is that okay? So how do we see that? So if we somehow map this vertex with this one, map this vertex with this one, map this vertex with this one, and map this vertex with this one, then we will see that whenever there is an edge between, let's say, these two vertices, then there will be an edge between the mapped vertices. Okay, so isomorphic, if we want to describe it formally, we will see that if two graphs are isomorphic, then there exists a bijection, let's say F, between the vertices. So we are having a bijection of the vertices. One vertex mapped to a distinct vertex in the other graph, such that whenever the original vertices, let's say x and y, they are adjacent, then the mapped vertices, fx and fy, they are adjacent. Is that okay? So if you check carefully, although all these graphs here, they look rather different, but then they are actually isomorphic to each other. In particular, so this graph is known as the Peterson graph. So this graph has a lot of, it is used as a lot of examples in some of the graph theory lemma or graph theory results. But then you see that all the graphs that I have included here, they are actually isomorphic graphs of this Peterson graph. So somehow there exists a mapping between the vertices from this set to the vertices here, so that when you see an edge here, then you see the corresponding edge there. Okay. Now we can talk about two graphs, they are isomorphic. Then if they are not, then they are not isomorphic. So for instance, we are claiming that this graph and this graph, they are not isomorphic. So can we see a reason why? So is there a particular reason why they are not isomorphic? So let's try this. Okay. So if they are isomorphic to each other, then there will be a one-to-one correspondence between the vertices, such that the resulting edges, corresponding edges, will be also one by one corresponding. So in particular, what I want to claim here is that, so here there is a vertex with two incident edges. So this vertex has degree 2. So if this graph is an isomorphic graph of this one, then this vertex should be mapped to some vertex that is also of degree 2. Now, if this is the case, then let's take a closer look on the left-hand side graph. So the left-hand side graph, there are only two vertices with degree 2. But on the right-hand side graph, there are three vertices with degree 2. So what does that mean? So it means that these two graphs cannot be isomorphic. They cannot be of the same structure. Now, how about this one? Okay. Now, if you look at this one, then although there's just, let's say it looks like there's just one edge difference here, but then they are also not isomorphic to each other. So is there a way to show that it is not isomorphic? Now, if we do the same thing as before, counting vertex degree, then it's not good, because in this graph there are 1, 2, 3, 4 vertices with degree 2, and for this graph there are 1, 2, 3, 4 vertices of degree 2. Yeah, so it doesn't look like we have an easy proof. But on the other hand, on this graph, there are the two vertices with degree 2. That at least we can find vertices of degree 2, they are joining to each other. But then the vertices of degree 2 in the right-hand side graph, they are not joining to each other. So in such a case, this graph and this graph should not or cannot be of the same structure. Because if they are of the same structure, each of the vertex degree with degree 2 must be mapped to one of the vertices here. And so there must be one vertex mapping to this one vertex mapping to this one, but then we don't see any edge joining. So we have edge joining these two vertices, but then we don't see any edge joining the vertex with degree 2 on the right-hand side. So they are not isomorphic. Okay, so somehow when we want to show that two graphs are of the same structure, then it is easy. We can just give a particular bijection showing that this bijection is correct. But when we want to show that two graphs are not isomorphic, then we want to find out something that is related to its structure so that we can differentiate one graph with the other. Okay, so this is the end of lecture 13. So let's look at lecture 14. So lecture 14 is a set of slides that talks about two topics, the Euler paths and the Hamiltonian paths. We will not cover Hamilton paths or Hamiltonian paths for the regular class. So this concept will not appear in the exam. If we will talk about this if we have time later, but we will first focus on Euler path for right now. So first of all, what is a path? A path is a sequence of vertices such that between the two vertices that we talk about, then there is an edge. So for instance, W, X, Y, Z, X, this sequence is a path because if you look at, we can actually think of the edge as a road. We can go from W through a road to X, and then through an immediate road, direct road to Y, and then Y to Z, and then Z back to X. Is that okay? And this is a path of length 4. The length counts the number of edges. Okay, so it doesn't matter. So a path, you can have a sequence of vertices. So the vertex itself can repeat. So we have X here, and then we have X here as well. But then we have also something called a simple path. So a simple path is a path such that we are not visiting the same vertex again. Okay. Now, if a path begins and ends at the same vertex, then it is called a circuit. So W to X to Y to Z back to W. This is a circuit. Okay, so this is like a cycle, a closed loop. And this circuit here has length 4. We also count the number of edges. Okay. Now, we have another example of showing non-isomorphic. So we have two graphs here. We want to show that this graph and this graph, they are not isomorphic to each other. Now, one thing that we can see here is that on the left-hand side, we have a circuit of length 3, but on the right-hand side, we don't have a circuit of length 3. So in this case, these two graphs cannot be of the same structure. Yeah, because if they are of the same structure, there must be a vertex corresponding to this one on the right-hand side. There must be a vertex corresponding to this one on the right-hand side. And there must be a vertex corresponding to this one on the right-hand side. And the three vertices corresponding to these three vertices on the right-hand should form a circuit. But then we don't see this on the right-hand side. So this cannot be an isomorphic graph of the left-hand side. Alternatively, you can also see that this graph is not a bipartite graph, but this graph, it is a bipartite graph. So if two graphs are isomorphic, they must also have the same structure. So if one is bipartite, the other has to be bipartite. But then we see that this is not bipartite, but this is bipartite. So in this case, these two graphs cannot be isomorphic. Okay. And then the next, we will talk about what is meant by a connected graph and a disconnected graph. So let's look at this graph. Edges, you can think of them as rows. So and then vertices, you can think of them as cities. So if we can travel from each city to another one by using the rows, then the graph is called a connected graph. So this one is connected. So you can reach every vertex from every other by using the rows here. Now this graph, it is disconnected. Yeah, for instance, I cannot reach any other city starting from this one. There is no road joining between them. Okay, so this is the disconnected graph. And then we can also talk about what is meant by a connected component. Okay, a connected subgraph inside the graph is called a connected component. But then when we talk about connected subgraph, we want to talk about the maximal one. So we will not just pick 1, 2, 3, 4, 5, these 5 vertices and call them as connected component. We will pick all the possible ones that everyone can join to each other together, include them together as one connected component. So in this graph, there is one connected component. In this graph, this is the disconnected graph, but this disconnected graph is formed by this connected component together with this connected component together with this connected component. Okay? Okay, we can now talk about what is meant by Euler path and Euler circuit. So this is a map of a Prussian city called Königsberg in the 18th century. So in this city, there is a river called the Prego River, and then Prego River is something like this. So it actually divides the land into a few regions. So this is one region, there's an island here, that's one region, and there's another region here. Okay. Connecting these regions, there are 7 bridges. So they are labeled as the green part here. So there are 7 bridges. And then one question here is that can we start at certain location, let's say this one, and travels each bridge exactly once and come back at the original location. Now it turns out that this is let's say we find a way to travel these 7 bridges. Maybe this is the way. We start from here, go to this one, back here, go from here, and ending at here. Then we will see 2 things. We are not ending at the same place as we start, and then there is one bridge here that we have not walked. So is it possible? So this problem is first studied by Euler. So what Euler tries to capture this problem is he made this problem into a graph problem. He used a vertex here to represent the region. So this is a big region here. It is represented by this vertex. The island here is represented by this vertex. This region is this one, and there is another one that looks like an island by this one. And then he uses edges to represent these bridges. So we can see that there are 7 bridges here. Now the problem here is, can we start from a certain vertex and then go across all the bridge exactly once and then ending back? So is there a circuit that travels each edge once and only once? Okay, exactly once. So if this is the case, then we call that we have an Euler circuit. So the concept of Euler path is, can we start at a certain vertex and then walk along this edge so that all the edges are included? We don't care about the starting and ending. So as long as we can do so, this is called an Euler path. And what is an Euler circuit? An Euler circuit is an Euler path such that it is also a circuit. So can we start from a certain vertex, walk along every edge exactly once, and go back to the original vertex? Okay. And then we have a theorem. So first of all, for a graph that has an Euler path or an Euler circuit, then it has to be connected. Yeah, assuming that there is no isolated vertices. Okay. So but here we focus on the case where whether a graph has an Euler circuit or not. So Euler gave this observation. He found that a graph has an Euler circuit if and only if this graph is connected and every vertex has even degree. So this is a case that we have an Euler circuit, and let's check the degree. The degree here is 2, 4, 4, 2, 2, 2. So every vertex has even degree, and it is connected. So Euler says that it has an Euler circuit. Now, this theorem contains 2 parts. One part is if, the other is only if. So first of all, the if part is the only if part is very easy. So if a graph has an Euler circuit, then every vertex must have an even degree. So it is rather easy. We just walk along the Euler circuit, and we find that every time we enter a vertex, we must need to go out. So in such a case, every in corresponds to every out, so that each vertex must be having exactly even number of edges joining to it. Now the only exception is the starting vertex, but the starting vertex is we start from the first time that we start. Okay, so this is a starting vertex. So for the starting vertex, we go out, but every time we come back, unless it is the end, then we must go out again. Every time we go in, then it must go out again, unless it is the ending edge. So the first edge and the ending edge forms a pair, and then all the intermediate edges going in maps to going out. So it means that even the initial edge, that initial vertex that we start this Euler circuit must also have even degree. So one part is rather easy. So here we call it the only if part because we write this first. Euler circuit implies even degree. It is easy. Now why even degree implies Euler circuit? Then we can prove this by induction. So suppose that we have a graph such that we know that whenever the graph is connected and having very few number of edges, then it must have an Euler circuit, something like this. But now we have a larger graph, each vertex has even degree, and then how can we prove that it must have an Euler circuit? So what we do here is we start from any vertex and walk until we go back. We must be able to do this because of the pigeonhole principle, because each time we must be using one edge, and then we go out again, then we must hit this edge, hit this vertex eventually, because this is also the vertex that has currently the odd degree. All the other vertices, it must have even degree somehow. You can check the OCW recording to see why we must have a way to go back to itself. Now we start from any vertex and walk along so that until we go back to itself, then it forms a circuit. If this circuit includes all the edges, then we are done. We have an Euler circuit. If not, then we take away this circuit, so we have the resulting graph. The resulting graph will be formed by disconnected components, but then each one of them will have all the vertices. Each one of them, the vertices must also have even degrees. Yeah, you can see why, because we are taking away a circuit so that the number of edges that we are removing from a vertex is always an even number. So in such a case, then we have a component here, but each component, it is a smaller component, and each vertex has even degree. So by induction hypothesis, we can form an Euler circuit here, we can form an Euler circuit here. And finally, to see that the whole graph, the original graph, has an Euler circuit, that's it's easy. We can walk along the original graph at the first circuit that we try to remove, but when we hit a vertex that is joining some edge that is not removed, then we go along this vertex to walk along all the edges joining to it using the, let's say we walk along this red one, and then go up to this vertex U, and then we see that we have not walked along the other edges outside C, so we can do so by walking along these green edges here. Yeah, this is done because of induction hypothesis. There is a Euler circuit here, and then we go back and continue back to the red circle, and then walk along this orange one, and then go back to the red one. So in that case, we form a bigger circuit, and then this circuit will include all the edges. So that's why we will have an Euler circuit in the end. Okay, now this handles the case where this, excuse me. So this handles the case where the graph has an Euler circuit. So what happens when we only want to talk about the graph that has an Euler path, but no Euler circuit? Then the idea here is that if it has an Euler path, but it doesn't have an Euler circuit, then if we add an extra edge joining the beginning vertex to the end vertex of this path, then it must form an Euler circuit. So an Euler path without an Euler circuit means that it is an Euler circuit by removing exactly one edge. So we have then this corollary. A connected graph has an Euler path but not an Euler circuit. This happens if and only if every vertex has even degree, except that two of the vertices, they are having odd degree. So the two vertices having odd degree corresponds to the beginning vertex and the ending vertex of this Euler path. Okay, so that's for the Euler path and Euler circuits part. So the remaining slides, we are talking about Hamilton path. So if you are interested, take a look. And finally, we are going to talk about planar graphs. We will talk about part of them today, and then there are some other interesting results. We will leave them as the next week's progress. So we want to define what is meant by planar graph, and importantly, we want to give the Euler planar formula. Okay, so what is a planar graph? Okay, a planar graph is an undirected graph such that we can draw the graph on a plane, on a piece of paper, without any edges crossing. So this graph is having four vertices, and then we have between any two vertices there is an edge. So this is actually a complete graph with four vertices. So this is one way to draw this, but then we can also draw it in another way like this. Is that okay? So if a graph has the way to draw such that there is no edge crossing, then this graph is called a planar graph. This is a planar graph. This is a planar graph. And the way that we draw it without edge crossing each other is called the planar representation of the graph. So this is a planar representation of K4. But notice that the planar representation is not unique. So we have some other planar representation of K4. So all of them, they look different. But what Euler has, so Q3 is a three-dimensional cube. It is also a planar graph. K1n and K2n, they are also planar graphs for every n. So this is K15. So the coloring here is for illustration purpose. So we will see that all the blue vertices are in one group and all the white vertices are in the other group. Okay. Now, when we have a planar representation of a planar graph, then the plane is split into regions. And one of them may have no boundary, so we call it an infinite region. So for instance, if we have this is a representation of K4, so we will see that there is a region 1. So region 1 is bounded by these three edges. Region 2 is bounded by these three edges. Region 3 is bounded by these three edges. And region 4 is bounded by this edge, and this edge. But then we are talking about this infinite region. Okay? And for this one, this graph, it has two regions. One region here that is bounded by this edge, and the other region that is the infinite region. Okay, so what is Euler's planar formula? So Euler's planar formula, in the specific case, we handle the connected case. So we assume that we have a connected graph, and this connected graph is a planar graph. That means that all the edges can be drawn without any problem, so that there is no crossing. Okay? And then let G be a planar graph, connected one, and then focus on any planar representation of G. We use big V to represent the number of vertices, big E to represent the number of edges, big F to represent the number of regions. We must have V plus F is equal to E plus 2. So let's take a look at this example. In this example, there are 4 vertices, there are 6 edges, and how many regions? 1, 2, 3, 4, 4 regions. So V is 4 f is 4 and e is 6, 4 plus 4, it turns out that it is equal to 6 plus 2. This is this is a three-dimensional cube drawn in the planar representation. There are 8 vertices here, and there are 6 regions, and then there are 12 edges. So we see that 8 plus 6 is equal to e plus 2. So one way to remember this formula, this is what I use, is this is very famous Euler, and then this 2 is the symbol. Okay, so this is very famous Euler So e plus f is equal to e plus 2. And how can we show this? We can actually show this by induction. We are doing this process. So we have a graph that we want to produce in the end. What we are going to do here is we add the edge one by one, and then keeping anytime the graph that we see is a connected graph. So when we start with the first edge, this edge will join exactly 2 vertices. So these 2 vertices will be the v is equal to 2, edge is 1. Then at this moment, the number of region is also 1. So v plus f, which is 2 plus 1 region, is equal to 1 edge plus 2. So at the beginning, when we just have 1 edge, then it is true. The formula is correct. But then for all the afterward steps, then we can only have 2 of the cases that happens. One is we are adding a new vertex joining by an edge to the original connected component. So we call this case 2. We add a vertex by joining this vertex with an edge to some existing vertex. Now, if this is the case, then we will see that the number of regions will not increase. But on the other hand, the vertices will increase by 1, and the edge will also increase by 1. So we will see that v increased by 1, f remains unchanged, e increased by 1, so that the formula is still balanced. The other case will be we are adding an edge without adding a new vertex. That means what? That means that we are joining 2 vertices together. Now, by joining 2 vertices together, then it means what? It means that there will be a new region formed. Originally, there is a big region, but then we are cutting this region into 2 parts. So in such a case, we add an edge without increasing the vertex, but increasing the region. So we add an edge without increasing the vertex, but increasing the region by 1. So we will see that the formula is also balanced. In each case, we either is adding a new vertex with a new edge, or adding a new region with a new edge. So in this case, the formula is balanced since the beginning. So in the end, the formula must be balanced. Okay, so this is Euler's planar formula. Okay, but for Euler's planar formula to be used, then we need to start with a certain planar representation, and then we count the region and so on and so forth. But so if we just have a graph without any knowledge about whether it has a planar representation or not, then we just know only the vertex and the edges. So we only know the number of vertices and the number of edges. So Euler's planar formula can help us to give some corollary. So first of all, it tells us that if a graph is connected and simple and planar, so it is a connected simple planar graph, then it cannot have many edges. E must be less than or equal to 3v minus 6. So why it is true, then you can go through the OCW recording to see. It is not difficult. But then, assuming that we have this result, so every connected simple planar graph, we must have E less than or equal to 3v minus 6 in general. So vertices are a lot. So this is the general case. Specific case, we have different cases, but then when we have more vertices, v is greater than or equal to 3, then the number of edges cannot be a lot. Then immediately, we can show that K5 cannot be a planar graph. Now, showing something is not planar is not easy because we need to convince people that no matter how you draw, there are infinite many ways to draw a graph on a plane, right? So no matter how you draw it, there is no way that there is no edge crossing each other. But with this observation, we will see that a planar graph cannot be having a lot of edges. So we just plug in the formula here. So for K5, there are 10 edges, there are 5 vertices. But then we will see that E is greater than 3v minus 6. 3v minus 6 is 9. 10 is greater than 9. So it doesn't satisfy this E is less than or equal to 3v minus 6. So in such a case, immediately we see that it is not planar. So K55 is not planar. We can also see that K33 is also not planar. But then we need to have a stricter relationship here. So this is for connected simple planar graph. We can have a similar result for connected simple bipartite planar graph. Okay, so if the graph is bipartite, then the number of edges is even. So it's even, let me see, it's even fewer, I think. So in such a case, we can see that K33 is also not planar. So these two graphs, K5 and K33, they are very special. They have important positions when we talk about planarity of a graph. So we will also see this again, revisit these two graphs again later when we talk about some other things. Okay, so that's all for what I want to introduce today. If you find some details missing, then please go to the OCW recording to see more. So let me quickly check if you have any questions. If not, I think that's all for today. Thanks for coming. And we will meet again next Monday. Okay?